Welcome to our channel Electrical and Control Engineering. We provide the research simulations in the field of optimization, especially power systems and renewable energy resources. See the description for details. Students, today we will discuss the last lecture of renewable hybrid energy design. In this lecture we will discuss the result and discussion of renewable hybrid design, consisting of different renewable energy sources combination along with conventional sources to give us a very low levelized cost of energy. So first of all, let's discuss. We have simulated the following sample projects of renewable energy hybrid energy optimization. And there are many more, but we will only discuss the results of 3 projects. And here we are only showing the 6 projects. And 3 of these we will also simulate, also discuss the results of these. The first one is the grid connected project. That has a solar energy, solar PV module, and hybrid car for home load optimization. This project is a small grid connected home project. So we can optimize the system that has a solar, hybrid car and load. The second one also a grid connected optimization project. That is consisting of wind and battery system. Wind power available and battery bank is there. This project is also connected to a grid. This also small home optimization project. And the third one is an optimization of renewable energy sources. It consists of solar energy in combination with other conventional sources, like biomass, gasifier. This project doesn't include the wind. This standalone mode project. Fourth project is also a standalone mode. It consists of solar energy and battery sizing. We have to optimize the project design to meet the load demand. Having specific solar PV module. We have to optimize the size of the solar PV module and the battery banks. The next one, standalone project, that consists of wind energy, solar energy, battery banks. So we have to optimize the size of the battery bank, the solar and wind resources. And the last one is also standalone project, which consists of wind energy, solar energy, battery ban, and DG. Diesel generator is used as a backup in standalone mode. We have to optimize the combination of this wind energy, solar, battery bank and the operation of DG. If you need similar projects, you can email us given the description. We will help you. So let's simulate a project. First of all, let's discuss a project that consists of a solar PV module and battery bank. We have to optimize the size of the solar PV module and battery sizing. This is standalone project. So let's run it. So it will take a little time. After some time it will converge and will give us the results. Currently running. It has 2 variables, x1, x2. x1 is the size of the PV module, that of solar plant, and x2 is the size of battery bank. It took almost 8 minutes to converge the fitness function. Here you can see that the simulation is converged to x1 as a 765.99 means 766, and the second one is 723. It means for the specific load for this hybrid optimized project, we need 766 solar module of the PV module of specific rated power that we have used. And number of battery units required are 724. So let's discuss the results of all. This is a weekly plot that just show you the effectiveness of this optimized design. This one. This color, the bluish one signal, is the load. This color like a red one, that one is a battery discharging. And the black one is the solar energy generated. So you can see that in the daytime in the solar is available, this load is met by the solar PV module. At the same time extra energy is being provided to the battery bank to charge it. In off timing, when the solar energy is not available, The battery banks, charged in the daytiming, are used to provide energy to the load. So you can see that in the off-day timing, battery bank is providing energy to the load. So the next graph is about load and charging of the battery, and the black one is the total generator power plus battery discharging. First thing that you can see that this greenish line is always below this black dotted line. So the load is met each time. So you can see that in daytime the solar energy is available, load is met by solar, otherwise by battery bank. So we are ensuring that in each interval of time that the load is met either by the battery bank or the solar energy available. So this graph with when sufficient solar energy is available. You can see that the extra energy is being provided to the battery bank to charge it until is fully charged. The next graph is about charging and discharging characteristics of the batteries, showing the specific 1-week interval. You can see that the charging and discharging of battery, 400% round-trip efficiency battery. This charging area should be equal to this discharging area. We can see it's equal, but it may look that this peak is a longer one. But the area of this area is equal to this one. So these energy should be equal if we integrate. What is B in? It shows the charging of the battery. B out means the discharging of the battery. After charging and discharging profile of the battery. The next graph is the SOC of the battery. When the solar energy is available, it is being provided to the load during this specific period. We have said that there is depth of discharge of the battery, to which the battery can be discharged. Here dot is 80%. So 20% energy will be there in the battery, at the minimum. So we can just see that when this bluish one, the solar energy is available, then the battery SOC is being increased. So it means a battery is being charged when there is a solar peak. That shows that battery is being charged in the daytiming. When the solar is not available, this battery is providing energy to the load. So its SOC going to decrease. Blue line is the battery discharging during off-day timing. At the same time SOC decreases as the battery is discharging. So this graph at the same time give the status of the battery, load, and generation demand. Next graph. Next graph shows the PV single module power profile. So for specific this week, you can see that when there is a sufficient solar irradiation is available, there is a solar peak. This showing the 24-hour interval. The next graph about SOC of the battery, so for a specific time it's showing the SOC of the battery. As the dot is 80%. So the battery can be discharged to 80%. So you can see that the battery been discharged status to 20%. So it can go 20%. I mean allowed one is 20%. This graph of the SOC is increasing and decreasing. When there is sufficient solar energy available, it is charged and its SOC increases. In off-day timing, the energy is provided to load. So SOC is decreasing. And the last graph is the levelized cost of energy versus the converter efficiency. So in our case the cost of energy is almost $0.235 per kilowatt hour. This is the generation cost. Power generation cost per unit of energy. So it can be seen that it decreases when there is an increase in converter efficiency. When there is 100% efficient converter is available for the same design. then the cost of energy can be reduced to $0.19 per kilowatt. The reason is that when the efficiency of the converter is increased, then it means that no loss of energy. So the more energy will be transferred to the load instead of loss. So overall cost of the energy will be reduced. The second project is about wind, solar, battery bank and diesel generator operation optimization. So it consists of wind, solar and battery bank, and diesel generator is also installed on the site. This optimization will select the hybrid design that will produce the power that has the lowest cost. So let's see the simulation. The simulation will give optimal size of wind, solar and battery bank. So let's run it. You are seeing that the simulation is running and it will take some time to converge. You can see that after several minutes running the algorithm is converged. So this is a PSO and GA solution. It can be simulated for ABC or whatever optimization algorithm we have, like differential evolution, GAABB and other global optimization methods. So its converged solution is that the wind turbines are 50 wind turbines of the rated capacity, almost 447 solar kilowatt and 82 battery units that we have used, so that's the optimal solution. And the annualized cost of the system is almost 1.6 into 10 power $5 per year, and the levelized cost of energy is $0.178 per kilowatt. So let's see the results. Results are more or less similar as shown in the previous one. This is the SOC increasing and then going down till the depth of discharge. 20% in this case. Next one is the battery discharging, total generation. Here in this graph the solar power is not shown in the generated power. And in the next graph similarly this is the battery charging, load and only wind power. And battery out. This not total power. Solar power generation and diesel generator power is not shown there. This is the battery characteristics, battery bank characteristics. Likewise previous the bin and bout energy should be equal. Similarly that's the load, wind, SOC, battery discharging profile. Likewise previous one. Here it is the load demand and renewable energy production. And this is the SOC of the system. Of the battery bank throughout the year. You can see it, this is the minimum SOC is of 20%. As our depth of discharge is 20%. And the maximum SOC is 100%. Thank you very much for joining us. If you have any project, you can contact us at the email given in the description. For any question do not hesitate to comment. Again, thank you very much.